Hello and welcome to this video about searching and recursion. Today we're gonna dig a bit more into actual algorithms or more complex algorithms, and I'll talk about why they work, and then I'll also show the code, and hopefully you'll be coding a bit yourself. If you are inspired by this lecture and like coding up these algorithms, then I encourage you to visit Project Euler, which is a website with a bunch of algorithms and exercises reminiscent of this, and it's really fun to sort of do them. I hope you will think it's fun too. We'll in this lecture we'll focus on search algorithms, so searching for a number or a specific kind of element in a list typically. And we'll also talk about recursion, which is basically having a function that calls itself. There will also be some advanced stuff, which is sort of optimizing stuff, basically. So search. First algorithm we'll go through is linear search or sequential search. The problem we have is we have to check whether some element is inside a list, so whether it's present, basically. So the input is the list and the element we want to check for, and the output is just Boolean, is just whether that is true or it's not true. So whether the element is in the list or it's not in the list. And the algorithm in pseudocode is just you start by setting the variable found to false. So this will be our output variable at the end. And in the beginning we have not found the element, so we set it to false. And then you go through all the elements in the list, compare it to x, and if x is equal to y, so if x is equal to the element, then found is true, and you break the loop and you return true. And this is all the third step, you return found, whether or not the element is in the list. So if you never find x equals to y, the elements of the list, then you just go through the loop and jump out of the loop. You can do two things now. You can pause the video and see if you can write up this code just using the pseudocode. You can also continue the video and look at me trying to write it up without looking at the answer. Or you can, those are your two options. Try to do it yourself or look at me doing it. If you have done it yourself, then you can sort of skip me doing it. I'll probably make a mistake at some point. Try to do that. I encourage you to do it yourself. But if you're completely don't know what to do, then we can do it together. So we follow the first step. Found is equal to false, and then we loop through the list for y and l, and then we say if y is equal to x, found is equal to true, and we break the loop. So what I did was I followed the first step, which is pretty easy. Then I loop through all the elements in L and call them y, and if y is equal to x, then I will set found to true, and I will use the break to break the loop, so I don't iterate through all the elements if I found it. So for example, if the first element is the one I'm looking for, then I don't want to go through all of them. So I break the loop there, and then at the end I'll return found. So let's see if this works. Is 3 in the list? We can see no, it's not. Is 13 in the list? We can see yes, it is. So it works. That's nice. Okay. Yes. Now it's written up a bit nicer here, and it's actually also coded a bit different. I think the way I code it would be the most straightforward way, and sort of there are multiple ways to go about it. Here there's also better commenting, which is really nice. So what are the input arguments, and what is the return argument, and what type are they, and what are they sort of. So here it's coded as a while loop, So we have to have an initial counter, we have to know the length of the list, and we still create the found equal false variable. And then we do a while loop, so we don't have to do a break statement. We can just say while I is less than n and found is equal to false, then do this. And if L of I is equal to x, then you would iterate, or then you set found to true, and then this condition will never not be met anymore. So we go back to the while loop, and then you will break the loop because this condition is not true anymore. Then not found, because found is not true. And otherwise you increment to the list, and you get the exact same answer here. And yeah, in terminology, this is called a brute force algorithm, because you saw sort of saying, okay, the question is this element in the list? And then we're basically just going through every element of the list and checking if it's in the list, or if it's equal to the element we're looking for. And that's why I can call it brute force. It's sort of, it doesn't have any smart tricks or anything. It's just, what do you want me to do? I'll do that in the most straightforward way possible. Yeah, we can count the complexity. I'll talk about it fast because it's not that important. But in the best case, the element is the first element in the list, and then it's just one comparison and one assignment, and then you break the loop. In the average case, so if the element is present in the middle of the loop, so that would be n divided by 2, because you will find it on average, if the elements are random, you will find it halfway through, so you will make n comparisons. But we just call that n, because it's the same as some number times n, so it's linear. If the element is not present, then you will sort of go through the entire list and find out it's not present, and that will be n comparisons. And that's also the worst case, if the element is not present or it's last in the list. Another search algorithm is binary search. It's sort of, the problem is the same. Mainly you want to find whether an element is in a list, but now you know the list is sorted, which helps you a lot, so you can create a faster algorithm basically. Yeah, so the input is the same, a list L and a potential element X. The Boolean output is whether or not the element is in the list, and the algorithm is called binary search or phone book search. And what it is in the essence is just that you have sort of a sorted list and you want to find an element. So what you do is you start by checking the middle element and see whether or not it's what you're looking for. But if it's not what you're looking for, then you can discard half of the list, because you can say, okay, if what I'm looking for is larger than what I found in the middle, then I sort of know that all the numbers to the left of the middle point, they will all be smaller than the middle point, so they will also all be smaller than what I'm looking for. And then I can just sort of discard half the list, and then you have a new half the list, and then you can just do that again and do it again and do it again, keep like having the list until you find what you're looking for, or the list is empty and you don't find anything. Okay. So it's written up here in pseudocode. So first you set found to false, you locate the midpoint, and then you check whether or not the midpoint is the one, is the value that you're searching for. If it is, then you stop, and otherwise you do this. So if the midpoint is larger, then you restrict to the left point of the list. So if the midpoint is larger than what you're looking for, then you restrict to the left point of the list. Or if the midpoint is smaller, then you know what you're looking for is in the right part of the list. And then you return found. So the midpoint, you sort of, it has to be an integer, so you can't just divide the distance. You sort of have to round down to an integer if necessary. So this is just a equation we can use to calculate the midpoint, which uses integer division such that we round down. And you can see the midpoint between 0 and 4 is 2, and the midpoint between 0 and 5 is also 2, because we're rounding down. And then there are more examples So now again, you can try to do it yourself and pause the video. I'll also do it live here in code, and we'll see how that goes. Yeah, so pause the video now or go with me as I try to do it. Yeah, so I followed the first set, which just set found to false. Then I want to have an I and a j, so the I is 0 and the j is the last element of the list, which is the index of the last element of the list, which is the length -1. And then I want to do a while loop while I is, so I want to make sure the list does not become empty, and I want to make sure that found is still false, because when found is true, then I can stop the while loop. Okay, then I find the midpoint. Yeah, so this is the midpoint index, and I just copy this. So the index of the midpoint is this, and then I can do my comparisons. So if I say if L of midpoint is equal to what I'm looking for, then I can set found to true, and then we're done. Else if L of midpoint is larger, then I want to restrict my attention to the right part of the list. So if it's larger than x, then I only want everything to the, so if the midpoint is larger, then I want everything to the left of the list. So I can update my j here, instead of being the last element, then I can set it to the middle element, and I can actually just set it to the left of the middle element. So I set j equals to midpoint -1, and then I can do the opposite. If L is smaller, then I'm just updating I +1. Yes, and this should work. We'll see if it does. Yeah, it looks like it works. Awesome. And yeah, that was the fourth, was just returning. Yeah. So this was me writing up the code. Now you see sort of a more complete version. With the documentation, it has a print possibility, so you can sort of print what is actually happening. But the basic steps are the same. Initialize the found. Have the first, so this is what I call I and j, which is the first and last element. And then you do the same here. Calculate the midpoint. If you want to print it, then you print the list that you have left, and then these are the same. Yeah, I just use two else if statements, but you can also do it like this. This saves you a comparison, so it's actually a bit smarter. But otherwise it's the same. And then we can also print it just to see what's actually happening. That's kind of nice. Do print equals to true, and then we want it here. Yeah, so we start with the full list that we created up here. So this is the full list from 0 to 42, and then the midpoint is midpoint element is 13, and then we have the list, so we only look at this because we're looking for 3, and 3 is smaller than 13. Now the midpoint becomes 1, this is because we're rounding down. 3 is larger, so we only look at the right part of the list. The midpoint becomes 2, and then it becomes 8, and then we found out that 3 is not on the list, basically. Yeah, and we can see this gives the same answer also. Yeah, okay, so that's a print, and this is the same, just looking for 32. And you can see sort of it depends on the numbers in the list, on what number you're looking for, how many iterations the algorithm will have. So here there are 3 iterations. Here there's only 2 before you find the element. 3, there are 5. Sort of, yeah, it depends on sort of the elements in the list and what the midpoint is, and sort of how many times you have to have the list to find what you're looking for. So 42, which is at the very end of the list, will take more. And if you're looking for 17, or no, 13, then you will find it immediately because it's at the midpoint. Yeah. In terminology, this is called a divide and conquer algorithm, because you keep dividing the list that you're looking in, and then you're conquering because you find what you're looking for, or you find whether what you're looking for is in the list. Yeah, so then there's this thing about complexity, algorithm, or complexity, and the way you calculated this is sort of to say, you look at how many elements there are left after one iteration or comparisons, and if you do this iteratively, then you can see, if you assume that you keep splitting the list in exactly half, or you don't have to assume that you keep splitting it, you will split the list, or you're not necessarily splitting it exactly half, but approximately half. And if you do that j times, then there will be n, so how many elements there were originally, divided by 2 to the power of j elements left in the list. So when is there 1 element left in the list, you can sort of say, okay, when is this number equal to 1? If you multiply by 2 to the power of j and take logs on both sides and isolate j, then you'll find that j will be equal to log of n divided by log of 2. And that means there's 1 element left after log of n iterations or comparisons in the sort of average case. Because of course maybe you find it immediately, or you find it early, some stuff like that. But in sort of after this approximation, and then you say that the binary search algorithm has log n complexity. Yeah, so the intuition for the binary search algorithm is very close to the intuition for the bisection method, which is a method of finding a root scalar of a function. So you can imagine if you have some function which you know passes 0 at some point, then you can sort of find the root by using the exact same method. This will come up later, I just want to note it, and there's also a video on it if you're interested in that, but otherwise you'll learn it later in the course. Now I want to talk about recursion. So if you have some problem where you're told you have to sum the elements in the list, then it's pretty straightforward to just loop through the list, add each element iteratively, and then return the result. This will give us the correct answer, which is 25, if you add all of these things. But you can also use recursion, and recursion is basically just having a function that calls itself, and it's a nice way to sort of write less code. So if you find yourself doing loops where you're sort of doing iterative loops and sort of doing the same thing over and over again, then sometimes doing recursion can be really useful. It's mostly sort of these numerical problems where it can be useful. So in this particular problem, then you will use the fact that the sum of a list is the sum of the first element and the sum of the rest of the list. This sounds a bit abstract, but basically just saying, okay, the sum of all these numbers, all these numbers, is the same as 1 plus the sum of all these numbers. And why is that important? That's important because then you can just use recursion. And the way you use recursion is sort of just you add each element iteratively, but you're just making the original list smaller. So if you have a list of length 1, then you can just return that element, because then that's the sum of all the elements in the list. Otherwise, you can extract the first element and add the sum of all the remaining elements. So the answer is here. Maybe I'll also do here I'll print L to sort of show you what is happening. So we start with the full list 1 to 9. So I think this is easier. Alright. So this is the full list, and our first number is 1. Then as the next iteration, that's actually just the same. It doesn't matter. Okay. Sorry. Let me just print the list. That's easy. Okay, so we start with the full list. And then we have this 1, which we add to the sum of all these numbers, which is this list. And then and the way we want to calculate the sum of these numbers is just saying 3 plus the sum of these numbers, which is just 5 plus the sum of these numbers, which is just 7 plus the sum of 9. So what you're actually doing is you end up doing it having 9 plus 7 plus 5 plus 3 plus 1. But the code is sort of neat. This specific example, it's not that much harder, but it's sort of an easy example so that you know what recursion is. This is also a divide and conquer strategy. There's also this good video about recursion, talking a bit more about it and a more complex example that you can view if you're interested. Otherwise, I'll show you an example with Fibonacci numbers where it's a bit more necessary to use recursion now. Okay. So the Fibonacci numbers is a sequence of numbers that is defined the following way. The first two elements are sort of predefined. So first element is 0, zeroth element is 0, and the first element is 1. But all subsequent numbers are just the sum of the two previous numbers. And this is a case where recursion is really good or really nice. Because then when you want to find the Fibonacci of n, then you can sort of hard code the two first cases. And otherwise you can just refer back to the function itself, and then it will sort of go n-1 and n-2 until it comes back to these cases and add some of the numbers. So here it's just showing you the first Fibonacci number. So you have 0 and 1. Then you have f2, which is the sum of these two, which is just 1. f3 is the sum of these two, which is 2. And then f4 is the sum of 1 and 2, and sort of that way it moves forward. And it's much easier to write it this than having to do sort of nested loops that depend on n, and then you have like you will have a series of loops, which is never nice. Yeah, there is a caution of, about this. Yeah, this is why. So when you do this, you will end up calling the Fibonacci a lot of times, and you will end up calling the Fibonacci functions a lot of time for the same input arguments. So, for example, if I want to count the Fibonacci of some very large number, then it will suddenly take me a lot of time to run, and there is a much faster way to do it. There's an approximate formula, which is nice. So yeah, we'll just interrupt. As you can see, it takes a long time to run. We'll talk more about that in the advanced section. Yeah. And we'll, so you can see you have this approximate formula, which is fast and almost exact. But another way to speed up this recursion is using cache, which is basically just storing the answers for specific input arguments and then returning them instead of calculating them. And I'll show you that in the advanced section. It's not something that you'll be using all the time, but it's sort of a neat little trick. So the advanced section, if you want to watch it, I'll talk more about recursion and more about cache, and I'll talk about how to use recursion to search. But otherwise, thank you for watching. Yes, let's just dig into it straight away. It's relatively easy to implement caching, and as I said, what you're doing is you're just sort of storing your previous answers, and then just if you have already calculated the Fibonacci number for some number, or the Fibonacci number at some point, then you can just return that instead of calculating it a second time. So the second time performs no calculation, it just draws from memory. So we create in the global scope a dictionary with all our previous calls and answers, and then we can define it manually. So I'll show you how to do this manually to show you sort of the idea of what is happening, but there's also a really easy way to do it. So we want to check if we have already calculated the Fibonacci number for this n by checking if it's in the dictionary, and if it is, then we just return the dictionary value. And else we just do the same function as before, return the first two numbers. Maybe I should actually have, okay, I have. So we return the first two numbers, and here we just create an output argument, and otherwise we do the recursion if it's not the first two numbers. Then before we return our output, we also want to store it in the dictionary, such that next time we call it, we can just stop here. So this works well. I'll just turn this down, so you can see this takes 1.2 seconds, and if I increase, then it's going to take longer, while this cached version is much faster. So even for a larger number, then Python counts it at 0.0 seconds. So that's what's happening. An easier way to do it is to use a decorator, which you have not learned about before, but it's basically just a way to add functionality to a function without changing any code. And the cache decorator is easy to use, and what it does is you just sort of add it before the function with the add sign, or the snabelag in Danish. Cache is actually a function, and what's basically happening is it's redefining the Fibonacci cache function with something that in their code it doesn't look like this, but it's basically the same. It's just a bit smarter setup. So it redefines this function with a cache, with a sort of a memory of the answers, and checking if the answer is already in the memory. Yeah, so that's again this example. Well, this takes a long time to run, and the cache version is much faster. Yeah, and it's of course, and also, so if I redefine this function, then it will take, if I do it, I think 45 is fine. Just wanna not store all the answers. So here, yeah, then it takes 0.1. It's not a lot, but the second time it answers immediately, because then it's already in the memory of the function. Yeah, you should be aware though that using cache is not always efficient. It's sort of, you should use it when you have these recursion functions that call themselves with the same input multiple times. Then it's very efficient, as long as the output is a low memory output type, and the input is also a low memory output type, because there's a trade-off between memory usage and limiting the number of operations, basically. Yeah. Then there's binary search with recursion, so you can do the binary search we've talked about just using recursion instead. And the way it comes up is sort of that you're basically, when you're doing binary search, what happens after you find the midpoint is you're just doing, so you have the large list, then you find the midpoint. If that's not the true value, then you sort of split the list in two, and then you do binary search on the middle list. So I've already gotten a bit over time, so I'm just gonna show you the answer, but I encourage you to pause and try to figure this out yourself. Yeah, but otherwise I'll show you now how it's implemented. Yeah. So what it does is, in the recursive version, you sort of first have to check if the remaining list is empty, and then you return false that the answer has not been found. Otherwise, you find the midpoint, and if the midpoint is what you're looking for, then you return true. Otherwise, then you create a new list, so this half list, and then you want to check that list now using the same function as before. Yeah, and it's implemented like this, and it runs like a dream. Cool. Thank you for watching.